So in the last variety of lectures, what we mostly focused on was pulmonary ventilation, how air gets in and out of the lungs. Now what we're going to do in this next set of lectures is look at what's referred to as gas exchange. So we briefly touched on what gas exchange is in prior lectures. Just to reiterate the bare basics of gas exchange. What gas exchange is, first of all, you look at the air that exists within the alveoli. How did it get in there? Well, it came from the atmosphere into the alveoli through pulmonary ventilation, right? Everything that we just spoke about, right? The process by which air gets in and out of the lungs. Okay, so we have this air that exists inside of the alveoli, and then what is within the air, right? Part of what makes up the air is oxygen. And what you do with gas exchange is you look at how that oxygen within the air in the alveoli gets into the blood within the pulmonary capillaries that go past the alveoli. And then at the same time, what you do is you look at how carbon dioxide within that same blood, within that blood in the pulmonary capillaries, how does that carbon dioxide get from the blood into the air in the alveoli so that we can blow it off, right, through pulmonary ventilation? So that's what gas exchange is. It looks at the exchange of gases between the air in the alveoli and the blood in the pulmonary capillaries in either direction, right? For oxygen, it's going to be from the air within the alveoli into the blood within the pulmonary capillaries, and for carbon dioxide, it's going to be from the blood within the pulmonary capillaries into the air within the alveoli. Now, kind of like pulmonary ventilation, this seems like it should be a fairly simple process, but it's not at all. Both of these are going to be, as you're going to see, quite complicated. So to begin this process of truly understanding gas exchange, the first thing that you have to understand is what's called partial pressures. What are partial pressures? What you do with partial pressures is usually this is related to the air, okay? But it can be related to fluid too, as you're going to see, but that's more confusing, so let's just stick with the air, okay? We know, for example, that the atmospheric air at sea level has a total air pressure of 760 millimeters of mercury. That's the total air pressure. And here's the next thing that we know. We know that the air within the atmosphere is mostly made up of two gases. It's mostly made up of nitrogen and oxygen. Okay? Nitrogen and oxygen are the two main gases that make up the air within the atmosphere. So what is this whole, again, concept of partial pressures? Well, with partial pressures, the first thing that you do is you look at the total air pressure, and the total atmospheric air pressure at sea level is 760 millimeters of mercury. And then what you want to do is you want to figure out each individual gas's partial contribution to the total air pressure, right? That's where the concept of a partial pressure comes from. It's each individual gas's partial contribution to the total air pressure. And what we'll do is we'll go through these one at a time. All right, so if you look at the air in the atmosphere is made up of approximately 21% oxygen. And the air in the atmosphere is made up of approximately 79% nitrogen. It's made up of so little carbon dioxide that we're not even going to talk about it. Okay, so one more time, very important. Atmospheric air is made up of gases, right? And 21% of those gases within the atmosphere, within the air in the atmosphere, are oxygen gas molecules. Simpler way of saying that, 21% of the air within the atmosphere is made up of oxygen. And 79% of the air within the atmosphere is made up of nitrogen gas molecules. So the air in the atmosphere is 79% nitrogen. So now what does all of this mean? Okay. Again, if you've lost track, what we're trying to figure out here are partial pressures. We want to know oxygen and nitrogens. We're not really interested in nitrogen, but we'll do it mathematically anyways. We want to know oxygen and nitrogen's partial contribution to the total air pressure. We know that total air pressure at sea level is 760 millimeters of mercury, and we want to know how much does oxygen contribute to that total pressure, and how much does nitrogen contribute to that total pressure. That's what would be referred to as the partial pressure of oxygen and the partial pressure of nitrogen. Oxygen's partial contribution to the total air pressure, nitrogen's partial contribution to the total air pressure. And this is incredibly simple math, right? Think about it, okay? Total air pressure is 760 millimeters of mercury. And then you say, okay, well, oxygen makes up 21% of all the gases that are within the air. Thus, oxygen contributes 21% to the total air pressure. The air pressure is 760 millimeters of mercury, and 21% of the air is made up of oxygen, so oxygen contributes 21% to the total air pressure. So again, really simple math, right? You just say, what's 21% of 760? You do basically 0.21 times 760. And what do you find out? Oxygen's partial pressure within the air in the atmosphere, if we're at sea level, is about 160 millimeters of mercury. Oxygen's partial pressure within the air at sea level is 160 millimeters of mercury, approximately. Since the total air pressure at sea level is 760 millimeters of mercury, and oxygen makes up 21% of the gas molecules that make up the air, then oxygen must contribute 21% to the total air pressure, and that means oxygen's partial pressure, oxygen's partial contribution to the total air pressure is 160 millimeters of mercury. Very simple math, and I think a relatively easy concept. So even though, honestly, we don't care about nitrogen, let's do nitrogen, the partial pressure of nitrogen as well, just so that we can make sure that the concept is sitting well. Okay, so we know, yet again, total atmospheric air pressure at sea level is 760 millimeters of mercury. We also know that 79% of the air is made up of nitrogen gas molecules. Nitrogen makes up 79% of the air. And let me say this, this is always going to be true. Whether you are like on top of Mount Everest, where total atmospheric air pressure is a lot lower, or whether you were below sea level, where total atmospheric air pressure would be greater than 760, nitrogen always makes up 79% of the air, and oxygen always makes up 21% of the air. It's just always true. I just thought I would mention that. Okay, but again, we're trying to figure out nitrogen's partial pressure at sea level. Okay, we continually use sea level as a reference, so we're going to keep talking about it. But I still wanted to make that point about the fact that nitrogen always makes up 79% of the air and oxygen always makes up 21%. Okay, so what is nitrogen's partial pressure, okay, at sea level? Well, total air pressure at sea level is 760 millimeters of mercury. Nitrogen makes up 79% of the air. So nitrogen must contribute 79% to the total air pressure of 760. So what we would say is nitrogen's partial pressure, right? We want to figure out nitrogen's partial contribution to the total air pressure. We know that nitrogen makes up 79% of the air, and total atmospheric air pressure at sea level is 760 millimeters of mercury. So if we want to know nitrogen's partial pressure, all we have to do is figure out 79% of 760, which is what? 0.79 times 760. That's the math that we do if we want to figure out 79% of 760. And what do we end up finding out? Nitrogen's partial pressure is approximately 600 millimeters of mercury. Yet again, total atmospheric air pressure at sea level is 760 millimeters of mercury. Nitrogen makes up 79% of the air. And we want to figure out nitrogen's partial pressure, its partial contribution to the total air pressure. If nitrogen makes up 79% of the air and total air pressure is 760 millimeters of mercury, then nitrogen must contribute 79% to that total air pressure of 760. 79% of 760 is 600. 600 millimeters of mercury is the partial pressure of nitrogen at sea level. Its partial contribution to the total air pressure. So what this table is showing you is it's showing you, first of all, what's the partial pressure of nitrogen, oxygen, and carbon dioxide, as well as water, meaning water vapor. What's the partial pressure of these different gases within atmospheric air at sea level? Okay. So atmospheric air at sea level, we know, is 760. Total air pressure within atmospheric air at sea level is 760. Now, this table is slightly different, but it's the same principle. Okay. We know that nitrogen makes up approximately 79% of the air all the time. So nitrogen contributes 79% to the total air pressure of 760. So nitrogen's partial pressure is about 600. Nitrogen's partial contribution to the total air pressure of 760 is about 600. Okay, we know that oxygen makes up about 21% of the air. Okay. So what's oxygen's partial pressure? What's oxygen's partial contribution to the total air pressure? Well, if the total air pressure at sea level is 760 millimeters of mercury, and oxygen makes up 21% of the air, then oxygen contributes 21% to the total air pressure, and ultimately that comes out to about 160 in terms of a partial pressure. Oxygen's partial contribution to the total air pressure of 760 is 160 because it makes up 21% of the air. Okay, carbon dioxide, there's basically no carbon dioxide. It's so small, the amount. There's very, very little carbon dioxide that actually exists in the air in the atmosphere. So we can pretty much just call this zero. It's significantly less than 1%. Okay? What you actually end up finding, if you do it mathematically, there is some carbon dioxide that exists within the air at sea level. Clearly we know this because of plants. They need CO2 to survive. So there has to be some CO2 that exists within the air in the atmosphere, but there's very little. Okay? What you end up finding is that carbon dioxide's partial pressure, its partial contribution to the total air pressure at sea level ends up being like 0.3 millimeters of mercury. It's nothing. We might as well just call it zero. And then the last one is a little confusing, right? Because it's water. And you say, well, where's water coming from? Well, water can certainly exist in the form of a gas. We call that water vapor. So how much of the air is actually made up of water in the form of a gas, right, called water vapor? This varies depending upon the humidity of the environment that you're in. But let's say that the average is around 0.5%. Basically, a 0.5% of the air at sea level is made up of water vapor. This is obviously going to be greater than this on most days in a place like Florida, and it's going to be less than this on most days in a place like Phoenix, Arizona. But there absolutely is some water vapor, water in the form of a gas, that exists in the air in the atmosphere. Let's say on average it's 0.5. Okay, 0.5 meaning half of 1%. Okay, half of 1% of the air within the atmosphere is made up of water vapor, water in the form of a gas. Then what's water's partial pressure? What's its partial contribution to the total air pressure? Well, if water in the form of a gas makes up 1/2 of 1% of all the gases that exist within the air in the atmosphere, then water's partial pressure is around 3.7 millimeters of mercury, right? That's water's partial contribution to the total air pressure. Now, what was the point of going through all of that? Because look over here. This is the air that exists in the alveoli. What's total air pressure of the air within the alveoli? Well, we know in between breaths it's about 760 millimeters of mercury. It's the same as atmospheric air. Total air pressure of atmospheric air and total air pressure of the air within the alveoli in between breaths is exactly the same. But now what you can do is you can look at the partial pressures of these different individual gases, and you see they're quite different compared to atmospheric air. Now, why would that be the case? So as air moves from the atmosphere into the lungs, two major things happen to it. Here's the first one. As air moves from the atmosphere into the lungs, one of the things that happens to it is it becomes humidified. Okay. What does that mean? Well, in your respiratory system, in the respiratory tract, right, the conducting zone, there is a lot of water vapor, right? There's a lot of water in the form of a gas that exists all throughout the respiratory tract, right? We know that our whole body is made up of a ton of fluid, a ton of water, okay? So it only makes sense that throughout the respiratory system, the respiratory tract, there's a lot of fluid, right? There's a lot of water vapor within there. So the point is, as the air moves from the atmosphere into the lungs, what happens is a lot of that water vapor, a lot of that water in the form of a gas moves into the air that's coming in from the atmosphere. We say that atmospheric air gets humidified as it enters into the lungs. And what that really means, yet again, is that a lot of that water vapor that naturally exists in the respiratory tract, water in the form of a gas, actually moves into the air that's coming in from the atmosphere, right? As the air from the atmosphere moves into the lungs, the water vapor, water in the form of a gas that's already in the lungs, moves into that atmospheric air that's coming into the lungs. And what you end up seeing now is that air that came into the lungs from the atmosphere, that air that's now in the lungs is made up of a lot more water vapor than it used to be when it was air out in the atmosphere. So let me try to explain this. Air in the atmosphere, about 1/2 of a percent of the air in the atmosphere is made up of water vapor, okay? Water in the form of a gas. Air in the atmosphere, 1/2 of a percent of that air is made up of water in the form of a gas called water vapor. So if water vapor makes up 1/2 of a percent of the air within, at sea level, then what is water vapor's partial pressure within atmospheric air, okay, at sea level? Well, total air pressure at sea level is 760 millimeters of mercury. This is the air in the atmosphere. Water in the form of a gas makes up 1/2 of a percent of that air. So water contributes 0.5% to the total air pressure of 760. So water vapor's partial pressure is 3.7 millimeters of mercury. That's within the air in the atmosphere at sea level. That's water vapor's partial contribution to the total air pressure of 760 because it makes up 0.5% of all the gases within the air. Now, the air in the lungs. Okay? By the time that the air has moved from the atmosphere into the lungs, it's become heavily humidified. Lots of water vapor, water in the form of a gas, has moved into that atmospheric air as it comes into the lungs. And now, by the time that you're in the alveoli, approximately 6% of the air within the alveoli is made up of water in the form of a gas. It's made up of water vapor, right? That air is heavily humidified. That's what happens to atmospheric air as it moves into the lungs, okay? So the air within the lungs, the air that's actually now in the lungs that came in from the atmosphere, by the time that it's in the alveoli, about 6% of the air is made up of water vapor, water in the form of a gas, okay? So what does that mean? It means water vapor contributes 6% to the total air pressure. Okay? The total air pressure, the total pressure of air within the alveoli is, again, 760. And 6% of that air is made up of water in the form of a gas, water vapor. So now you say, well, what's water vapors? What's water's partial pressure? What's its partial contribution to the total? Well, water now makes up 6% of the air, right? That 6% of the air that actually exists in the alveoli. So that means water vapor contributes approximately 6% to the total air pressure. And what that comes out to is about 47 millimeters of mercury. That's water vapor's partial pressure within the air in the alveoli. Look at how much more it is compared to the air within the atmosphere. The partial pressure of water vapor, within the air in the alveoli is significantly higher than the partial pressure of water vapor within the air in the atmosphere. And that's just strictly because of the fact that so much water vapor that already existed within your respiratory tract and does exist within your respiratory tract moved into the air from the atmosphere that came into your lungs. And now, just simply put, if you look at the air that exists in the alveoli, much more of that air is actually made up of water vapor compared to the air that was in the atmosphere. So that's step number one. Step number two here. Okay. As the air from the atmosphere comes into the lungs, it mixes with air that has lots of carbon dioxide within it. Okay. As you're going to see, carbon dioxide is continually moving from the blood into the air within the alveoli. So as the air comes from the atmosphere, let's draw this. Okay. Here's the air coming from the atmosphere into the alveoli. Okay. CO2 is constantly moving into the air within the alveoli. So as the air from the atmosphere moves into the lungs, right? As the air from the atmosphere moves into the lungs, it mixes with air in the lungs that's much richer in carbon dioxide. We do blow a lot of that carbon dioxide off as we exhale, but not all of it. There's this thing called dead space within the lungs, and some air gets kind of trapped in the lungs every single time that we exhale, and that air has a high concentration of CO2. So as the air from the atmosphere, as we breathe it in, comes into the lungs, it mixes with air that has a higher than what we would expect concentration of CO2. So you can probably imagine what's going to happen here. Okay, take a look at this. Air within the atmosphere basically 0% of the air. It's a small number, but there is some, but basically 0% of the air within the atmosphere is made up of CO2. It's much less than 1%, so we'll just call it pretty much 0. All right. Now, as air moves from the atmosphere into the lungs and it mixes with air within the lungs that has a decent amount of carbon dioxide within it, what do you think happens to the amount of carbon dioxide within the air that just came in from the atmosphere? Clearly, as the air comes from the atmosphere into the lungs, it mixes with air in the lungs that's much richer in carbon dioxide, and now that air from the atmosphere that came into the lungs has a higher concentration of CO2 within it because it mixed with air in the lungs that has CO2 within it. Okay, so, oops, meant to circle this one, sorry. Take a look at this. Okay, this is the air within the alveoli. Okay, the air within the alveoli is made up of about 5% carbon dioxide. That's air that, has come in from the atmosphere. By the time that the air from the atmosphere gets into the alveoli, it goes from having essentially no carbon dioxide within it to having 5% of it be made up of carbon dioxide gas, right? And that's again because that atmospheric air has mixed with all this CO2 that already exists within the lungs. The CO2 keeps coming from the blood within the pulmonary capillaries into the lungs, into the alveoli. And as that air from the atmosphere moves into the lungs, it mixes with this air that's richer in CO2. So now if we look at the air, by the time that it's within the alveoli, has come from the atmosphere into the alveoli, now approximately 5% of that air is made up of CO2. So you say, all right, well, what's carbon dioxide's partial pressure? If we look at the air within the alveoli, the total air pressure is approximately 760 in between breaths. That's the total pressure of the air. Okay. Well, if we know that CO2 makes up 5% of the air, and this is air within the alveoli, then carbon dioxide must contribute approximately 5% to the total air pressure of 760. So you say, well, what's carbon dioxide's partial pressure? What's its partial contribution to the total air pressure of 760? Well, carbon dioxide makes up approximately 5% of the air, so it must contribute 5% to the total air pressure of 760. So its partial pressure, its partial contribution to the total is about 40 millimeters of mercury. The partial pressure of CO2 within the air in the alveoli is about 40 millimeters of mercury, and it's basically zero when you look at the partial pressure of CO2 within the air in the atmosphere. This is a long-winded way of telling you that as air moves from the atmosphere into your lungs, the air from the atmosphere as it moves into your lungs, right, lots of water in the form of a gas, water vapor, and carbon dioxide moves into the air. And by the time that you're in the alveoli, the air is made up of about 6% water vapor, and about 5% CO2. Both of those are substantially higher than compared to atmospheric air. There's basically no carbon dioxide in atmospheric air, and there's very little water in the form of a gas, water vapor. But since the air that comes into the lungs, right, since that atmospheric air that comes into the lungs mixes with a whole bunch of water vapor and carbon dioxide, the amount of the air in the alveoli, in the lungs, that's made up of CO2 and water is significantly higher. And ultimately, all of this leads us to the conversation of what's the partial pressure of oxygen within the air in the alveoli? And the answer is the partial pressure of oxygen within the air in the alveoli is significantly less than the partial pressure of oxygen within the air that's in the atmosphere, within atmospheric air. Well, why is that? Okay, look at atmospheric air. Atmospheric air, right, the total air pressure in the atmosphere at sea level is 760 millimeters of mercury. 21, approximately, percent of the air, 21% of the air is made up of oxygen. So oxygen contributes 21% to that total air pressure of 760, and its partial pressure, its partial contribution to the total is about 160. Okay, now what about the air within the alveoli? When the air moves from the atmosphere into the alveoli, since so much CO2 and water in the form of a gas, water vapor, moves into the air, moves into that atmospheric air as it moves into that atmospheric air as it comes into the lungs. By the time that you look at the air within the alveoli, much less of that air is actually made up of oxygen. Because so much CO2 and water has moved into the air, and they are now both making decent contributions to the total air pressure, right? When you look at the air within the alveoli, about 5% of it is made up of CO2, and about 6% of it is made up of water vapor. So now, less of that air is actually made up of oxygen. When you actually look at the air within the alveoli, about 13.5% of the air is made up of oxygen. And that's because so much more of the air, by the time that it reaches the alveoli, is made up of CO2 and water vapor. So the air within the alveoli, about 13.5% of it is made up of oxygen, compared to 21% of the air in the atmosphere that's made up of oxygen. So you say, what's the partial pressure of oxygen within the air in the alveoli? And you say, okay, well, the total air pressure within the alveoli is about 760. About 13.5% of the air is made up of oxygen. Much less of the air within the alveoli is made up of oxygen compared to the air that was in the atmosphere. Okay? And that's because there's so much more CO2 and water vapor. All right, so if 13.5% of the air within the alveoli is made up of oxygen, then oxygen contributes about 13.5% to the total air pressure of 760, which comes out to about a partial pressure of 100, right? Oxygen's partial pressure, its partial contribution to the total air pressure of 760 is about 100 within the air in the alveoli. Why is that? Why is the partial pressure of oxygen within the air in the alveoli 100 and the partial pressure of oxygen within the air in the atmosphere about 160? And the answer is, well, just simply because as the air moves from the atmosphere, into the lungs, right, lots of CO2 and water vapor move into that air from the atmosphere. And now more of that air from the atmosphere is made up of CO2 and water, so less of that air is made up of oxygen. Now only 13.5% of the air within the alveoli is made up of oxygen. So its partial pressure, its partial contribution to the total air pressure of 760 has to be lower, right? The partial pressure of air within the atmosphere and within the alveoli is still 760, both of them. But the partial pressure of oxygen within the air in the alveoli is significantly lower. And that's because oxygen only makes up 13.5% of the air. So it contributes 13.5% to the total air pressure of 760. So its partial pressure, its partial contribution to the total air pressure is 100 millimeters of mercury. Now, if you're wondering why we spent 15 minutes talking about this, it's because I think it's an important thing to understand, because way too often from my experience, and my experience as a student actually, however long ago that was, multiple levels of learning this, all I was told was that total air pressure in the atmosphere is 760, total air pressure in the alveoli is 760, and that the partial pressure of oxygen within the air in the atmosphere is 160, and by the time that the air moves into the lungs and into the alveoli, the partial pressure of oxygen within the air drops to 100, but the total air pressure is still 760. And then I usually got something like, well, it's because the air is humidified, and then we moved on. And I didn't have any idea what that meant. Okay. The partial pressure of oxygen drops by 60 millimeters of mercury by the time that it gets into the alveoli, and that's because it's humidified, whatever that might have meant. I had no idea what it meant for years, and I didn't want to do the same thing to you. I wanted to give you an opportunity to actually see why the partial pressure of oxygen within the air in the alveoli is less than the partial pressure of oxygen within the air in the atmosphere. It doesn't fundamentally change understanding any of the other concepts that are honestly coming up. You can get away without understanding why the partial pressure of oxygen falls as it moves from the atmosphere into the alveoli. You can get away without understanding that conceptually and still understand the other things that come. But that doesn't change the fact that if you don't understand why it actually happens, you're still missing a big chunk of this whole process. It's just a big glaring idea that is important and is there that never makes any sense. So my hope is, of course, as you progress through your career, that it makes sense to you why the partial pressure of oxygen within the air in the alveoli is 100. And now we will move on. So we've got this air within the alveoli. It came in from the atmosphere. And the partial pressure of oxygen within the air in the alveoli is 100 millimeters of mercury. Now I'm going to explain this in a lot more detail in just a moment. But the blood that is traveling past the alveoli, right, within the pulmonary capillaries, that blood, is initially, it's deoxygenated. Okay? It's lower in oxygen. There's a low concentration of oxygen within the blood, and there's a higher concentration of CO2 within the blood. That's what deoxygenated blood is. It's, O2 poor, CO2 rich blood. And it's traveling past the alveoli. So here's the thing. Within the blood, the oxygen that exists within the blood, specifically the blood plasma, it actually creates a partial pressure. There are gases that exist within blood plasma, within fluid, and they create a pressure within that fluid. We call it a partial pressure. Okay. I'm going to explain this in a lot more detail in just a moment, but let me tell you this. This is going to sound incredibly arbitrary, and we'll get into more detail as we go. So the partial pressure of oxygen within the blood plasma of the blood in the pulmonary capillary is 40. Okay. Yet again, we're talking about the oxygen within the blood that exists in the blood plasma. It has a partial pressure of oxygen of 40. What we say is the partial pressure of oxygen within the blood plasma of the blood in the pulmonary capillaries is 40 millimeters of mercury. And look at what we've got here. We've got a pressure gradient. Okay. What's the partial pressure of oxygen within the air in the alveoli? It's 100. What's the partial pressure of oxygen within the blood plasma of the blood in the pulmonary capillaries? Well, it's 40. That's a pressure gradient. Right? That's a partial pressure gradient, as we would call it. So you would say, well, where do you think oxygen wants to go? It wants to move down its pressure gradient. Okay? It wants to move from the air within the atmosphere into the blood plasma of the blood that exists in the pulmonary capillaries. Just to be clear, in case you've forgotten, why am I saying the blood plasma of the blood? Because blood is actually made up of red blood cells and blood plasma. So blood plasma is just part of the blood. That's actually going to become very important for this discussion here. Okay, so the partial pressure of oxygen within the air in the alveoli is 100. Right? for reasons I think that we have addressed in extensive detail. The total air pressure within the air in the alveoli is 760. 13.5% of the air is made up of oxygen. So oxygen's partial pressure is 100 millimeters of mercury. Now, the partial pressure of oxygen within the blood plasma of the blood in the pulmonary capillaries is 40 millimeters of mercury. So there's a partial pressure gradient that exists between the oxygen within the air in the alveoli and the oxygen within the blood plasma that exists in the pulmonary capillaries. So oxygen wants to move down its partial pressure gradient. It wants to move from the air in the alveoli into the blood plasma within the pulmonary capillaries. And that's exactly what it does. And this is where things get real confusing. So, you would look at this initially and you'd say, what would happen? You'd say, okay, well, the oxygen is going to move from the air in the alveoli into the blood plasma within the pulmonary capillaries. And what should that theoretically do in your mind? Like, you would say, well, that's going to cause the partial pressure of oxygen within the blood plasma within the pulmonary capillaries to rise maybe to 70. And that's going to cause the partial pressure of oxygen within the air in the alveoli to fall to 70 until they're both at equilibrium. But that's not what happens at all. What actually ends up happening is this. The partial pressure of oxygen within the air in the alveoli is 100. The partial pressure of oxygen within the blood plasma within the pulmonary capillaries is 40. So there's a partial pressure gradient. And what happens is oxygen begins to move from the air in the alveoli into the blood plasma within the pulmonary capillaries. And what ultimately happens is they're at equilibrium when they're both at 100. Now, that shouldn't make any sense, right? Because what you'd essentially be telling me is that oxygen moves from the air in the alveoli into the blood plasma, which makes sense because there's a gradient. But then the partial pressure of oxygen within the air in the alveoli doesn't fall at all, while the partial pressure of oxygen within the blood plasma rises, right? And then they're at equilibrium when they're actually both at 100. So there's a glaring issue here, which is why doesn't the partial pressure of oxygen within the air in the alveoli fall, right, as it moves into the blood in the pulmonary capillaries? Why doesn't it fall? Because oxygen is leaving the air within the alveoli and going into the blood within the pulmonary capillaries. How is the partial pressure of oxygen within the air in the alveoli not falling? So this brings us to a concept that tends to bother a lot of people that's called Henry's law. What Henry's law looks at is it looks at a gas within an air compared to a gas within a fluid and when they would be at equilibrium. That's what Henry's law focuses on. And that's what I'm going to try to explain to you is Henry's law. So here clearly we have a cylinder. Okay. Within that cylinder there is air. Okay. Let's pretend that the air pressure of the air within that cylinder, it could be the alveoli, is 760 millimeters of mercury. And now let's pretend that 13.5% of the air approximately is made up of oxygen. So oxygen would contribute 13.5% to the total air pressure. So its partial pressure, its partial contribution to the total air pressure would be about 100. So the partial pressure of oxygen within the air in this cylinder is about 100 millimeters of mercury. All right. Now you look at the fluid. Okay. There's actually no oxygen within the fluid. I realize I said that there was some oxygen within the blood plasma that's traveling past the alveoli, but this is not supposed to be literal. Obviously, we're looking at a cylinder here. This is just to understand the concept. So we're looking at this water. There's actually no oxygen at all that exists within the water right now. So you say, okay, if there's no oxygen at all that exists within the water, then what's the partial pressure of oxygen within that water? Nothing, right? It's zero because there's no oxygen within the water whatsoever. Okay, so what do we have? We have a big partial pressure gradient, right? The partial pressure of oxygen within the air in the cylinder is 100. And the partial pressure of oxygen within the fluid in the cylinder is 0, right? So there's a huge partial pressure gradient between the air in the cylinder and the fluid in the cylinder. The partial pressure of oxygen within the air in the cylinder is 100, and the partial pressure of oxygen within the fluid in the cylinder is 0. So clearly, right, oxygen wants to move in a particular direction, right? Oxygen is going to want to move from a high partial pressure to a low partial pressure. It's going to want to move from the air into the fluid. Oxygen is going to want to move down its partial pressure gradient. It's going to want to move from the air in the cylinder, where the partial pressure is 100, to the fluid in the cylinder, where the partial pressure of oxygen is 0. Okay. And what will that result in? It's going to result in the exact same thing that we saw between the air in the alveoli and the blood plasma in the pulmonary capillaries. What's going to happen is oxygen is going to move down its partial pressure gradient, and oxygen is going to move from the air in the cylinder into the water or the fluid in the cylinder, right? It's going to move from a partial pressure of 100 towards a partial pressure of 0. And what that will ultimately result in is the partial pressure of oxygen within the water, within the fluid, will rise to 100. But the partial pressure of oxygen within the air in the cylinder won't change at all. It'll stay at 100. And they will be at equilibrium when the partial pressure of oxygen within the air is 100 and the partial pressure of oxygen within the water or the fluid is at 100. Yet again, you look at this and you say, that doesn't make any sense, right? Shouldn't the partial pressure of oxygen within the air decrease as it moves from the air into the fluid, right? Because oxygen is being lost from the air. So shouldn't the partial pressure of oxygen within the air decrease? Why doesn't it? So to understand this, you have to go back to one of the fundamental concepts in this class, which is also a fundamental concept in chemistry, which is what makes something polar and nonpolar. Okay. Oxygen, atmospheric oxygen, is two oxygen atoms bound together covalently. And they share electrons perfectly because they're both equally electronegative. So atmospheric oxygen, two oxygen atoms bound together, is unbelievably nonpolar, right? If we look at atmospheric oxygen, two oxygen atoms bound together covalently, the electrons are shared around the molecule perfectly. There's no uneven distribution of electrons around an atmospheric molecule of oxygen. There's no positive and negative side. That doesn't exist. There's a perfect distribution of electrons around this atmospheric oxygen molecule, two oxygen atoms bound together. So atmospheric oxygen is incredibly nonpolar. Now, what about water, which is H2O, one oxygen and two hydrogens. Okay. Water, H2O, one oxygen, two hydrogens. The oxygen is much more electronegative than the two hydrogens, so the electrons are scattered around the oxygen, and the protons are more distributed towards the hydrogens. So you end up with a molecule that is very polar. Water is polar, right? It has an uneven distribution of electrons due to the more electronegative oxygen atom pulling the electrons towards itself. The electrons are negatively charged, so the electrons are more clustered towards the oxygen side and less towards the hydrogen side, and you end up with a polar molecule, right? A molecule that has charges on each side, right? One side of the molecule is slightly negative, one side of the molecule is slightly positive. So you need to look at what we're trying to get to interact here, right? We are trying to get atmospheric oxygen, which is incredibly nonpolar, to interact with water, which is incredibly polar, right? All of these oxygen molecules, all of this atmospheric oxygen, all these dots, they are all nonpolar. And the water, right? The water in the cylinder is all made up of H2O, water, which is incredibly polar. And what are you trying to get to happen right now? You're trying to get the atmospheric oxygen molecules, right? Two oxygen atoms bound together, which is an unbelievably nonpolar molecule. You're trying to get those atmospheric oxygen molecules, which are nonpolar, to move into the water, which is incredibly polar. So should this happen to any meaningful degree? And the answer to that is no. The two of them don't go together. Atmospheric oxygen and water do not coexist very well. Atmospheric oxygen is very, very nonpolar, and water is incredibly polar. The two do not go together well. They don't bind and coexist with each other to any meaningful degree. And this is where the concept begins to make more sense. So here's what's going to happen, right? You've got this air that exists within the cylinder. Okay. Let's say the total pressure is 760. Okay. 13.5% of the air is made up of oxygen. So oxygen's partial pressure is 100 millimeters of mercury. Its partial contribution to the total air pressure is 100. Okay. Now, within the fluid, there's no oxygen. So the partial pressure of oxygen within the fluid is nothing, non-existent. Okay? So there's a big partial pressure gradient. Oxygen wants to move from the air, where the partial pressure of oxygen within the air is 100, into the fluid, where the partial pressure of oxygen within the fluid is 0. And it does. But here's the thing. The oxygen within the air and the fluid do not coexist with each other well, right? The oxygen, atmospheric oxygen, is incredibly nonpolar, and the fluid, the water, is incredibly polar. So what happens is you have to understand there is some polarity to all molecules, okay? Even when we say something is nonpolar, like, again, atmospheric oxygen, that doesn't mean that it doesn't have any polarity whatsoever. It's not literally nothing. There's some polarity to oxygen, atmospheric oxygen. There's just hardly any of it there, so we call it nonpolar. Okay, but there are degrees of polarity, as you're going to see as we progress through this. So even atmospheric oxygen has some polarity, even though it's incredibly small. So the point is, oxygen absolutely can move into water, and it can bind with water to some degree, but it's incredibly minor. And what ends up happening is this. Some oxygen will move down its partial pressure gradient. It will move from the air in the cylinder, where the partial pressure of oxygen is 100, into the fluid, where the partial pressure of oxygen is initially nothing in the fluid. And some oxygen molecules will move into the fluid. But this is what happens, and this brings us to the concept of the partial pressure of a gas within a fluid. Basically, you think about it, the theoretical concept is that the gas creates pressure within the fluid. What that really means is kind of how much does the gas bounce around in the fluid? Okay. If the gas bounces around a whole bunch in the fluid, it creates more pressure within the fluid, quote unquote. Again, highly conceptual, theoretical sort of thing that we have here. But think of what would happen with regard to any oxygen molecules that were to move from the air into the fluid. The oxygen molecules, which are incredibly, again, nonpolar, and the water molecules, which are incredibly polar, would not coexist with each other very well. And this very, very nonpolar oxygen molecule would bounce around like crazy in all of this polar water. And that one oxygen molecule that went into the water would create a lot of pressure due to how much it bounces around, right? You've got this nonpolar molecule in a very polar environment. And that nonpolar gas molecule, the water molecule, kind of bounces around all over the place because it can't exist with the water very well. It's just shooting all over the place. It's bouncing all over the place because it's very nonpolar and the water molecules are polar and they don't coexist with each other very well. And that one oxygen molecule by itself generates a lot of pressure within that fluid. And it only takes a couple, in this example, one oxygen molecule moving into the fluid to drive the partial pressure of oxygen within the fluid up to 100. Let me say that one more time because it's incredibly important for the rest of this. If a molecule of oxygen, and that molecule of oxygen is very nonpolar, moves down its partial pressure gradient, right, from 100 to 0, and that molecule of oxygen, which is nonpolar, moves down its partial pressure gradient into the water where the partial pressure is 0. That molecule of oxygen, because it's very nonpolar, will bounce around like nuts in the polar water that it just went into, right? The medium that it just went into is all water, and water is very polar. So the oxygen molecule, which is very nonpolar, just shoots around like crazy, right? Sonic the Hedgehog or something. A pinball machine. I don't know. The oxygen molecule shoots around like crazy in all this polar water that it just went into, and it drives the partial pressure of the water up very easily to 100 millimeters of mercury. You don't need very many oxygen molecules to actually move into water to drive the partial pressure of the water up to 100. And that's because they don't coexist with each other very well. When any oxygen molecule moves into water, it will bounce around like crazy in the water and drive the partial pressure of oxygen within the water, within the fluid, up a lot. And thus, what you end up with is this. The partial pressure of oxygen within the water will rise to 100. And you didn't actually have very many oxygen molecules that went into the water. In this example, only one oxygen molecule went into the water. Obviously, it's going to be more than that, but the point is that very, very few oxygen molecules actually need to go into the water to drive the partial pressure of oxygen within the water up to 100. You don't need very many of them to do it because any one of them that goes into the water bounces around like crazy and increases the pressure dramatically within the water. That's what the theory is, at least. So you don't need very many oxygen molecules actually in the water to drive the partial pressure of oxygen within the water up to 100. And now they're at equilibrium. The partial pressure of oxygen within the air in this cylinder is 100. And the partial pressure of oxygen within the fluid in this cylinder is 100. So the gradient is gone, and now oxygen no longer has any desire to move from the air into the fluid because their partial pressures are exactly the same, and that determines which direction the gas will flow. But there are massive concentration differences, right? That's the point here, right? The partial pressure of oxygen within the air in the cylinder is 100, and the partial pressure of oxygen within the fluid or the water in the cylinder is 100. So the partial pressures are at equilibrium, but the concentrations aren't at equilibrium at all. The concentration of oxygen within the air is infinitely higher than the concentration of oxygen within the water or the fluid. This is what Henry's law tells us. It tells us that the partial pressures of a gas within air and a gas within a fluid can be at equilibrium, and their concentrations can be vastly different than one another. The concentration of oxygen within the air is significantly higher, I mean literally infinitely higher, than the concentration of oxygen within the fluid, but their partial pressures are at equilibrium. And the reason is because we didn't actually need very many oxygen molecules to move into the fluid to drive the partial pressure of oxygen within the fluid up to 100, which is the same as the partial pressure of oxygen within the air. Let's relate this now to carbon dioxide. It gives us another opportunity to try this again with a gas which is very nonpolar, but at the same time, it's also more polar than oxygen. I'm realizing that I never told you why the partial pressure of oxygen within the air never falls. And maybe it was obvious, but I need to say it. Okay, so the reason that the partial pressure of oxygen within the air stays at 100 and it doesn't fall is because basically no oxygen molecules actually left the air. That's the point. Okay. As oxygen moved from the air into the water, went down its partial pressure gradient, only a couple oxygen molecules, in this example, one oxygen molecule, actually went into the water or the fluid. And that was enough to drive the partial pressure of oxygen within the water or the fluid up to 100 because it bounces around like crazy and drives the partial pressure up very, very quickly with only one molecule of oxygen going into it. So the reason why the partial pressure of oxygen within the air doesn't fall is because really no oxygen has actually left the air, right? Only like a couple oxygen molecules actually left the air and went into the fluid, and that was enough to drive the partial pressure of oxygen within the fluid up to 100, right? To cause the partial pressure of oxygen within the fluid and the partial pressure of oxygen within the air to be at the same. So yet again, the reason that the partial pressure of oxygen within the air didn't fall at all is because, well, very, very few oxygen molecules actually left the air. So few oxygen molecules left the air that it didn't influence the partial pressure of oxygen within the air at all, right? It stays pretty much exactly at 100 millimeters of mercury. And this, of course, further explains why, the concentrations are so different while the partial pressures are the same, right? The concentration of oxygen within the air is much higher than the concentration of oxygen within the fluid when both of their partial pressures are exactly the same. All right, I just wanted to make sure to point that out before we now move on to carbon dioxide. Okay, here's CO2. Carbon dioxide, right? CO2, carbon and two oxygen atoms. CO2 is also a very nonpolar gas, but the point is it has more polarity than oxygen does. And this is important because I said this in the last slide, but I need to say it again. Any molecule gas that you hear is nonpolar, it's nonpolar, but that doesn't mean that it doesn't have any polarity. Both atmospheric oxygen and carbon dioxide are both considered to be nonpolar, period, end of story. However, each of them has degrees of polarity. And what I'm telling you is that carbon dioxide is more polar than atmospheric oxygen is. They're both considered nonpolar because they are, but everything that's nonpolar has degrees of polarity, and carbon dioxide is more polar than atmospheric oxygen is. Okay, that's step number one. Now, here we have this cylinder. Okay, this is going to be totally made up because it's not going to be like anything that we're going to discuss, but bear with me. Okay? Let's pretend that the total air pressure in the cylinder is 760. Okay? Just by chance, we artificially created this environment. So let's pretend that about 13.5% of the air is made up of CO2. So CO2 contributes 13.5% to the total air pressure of 760. So what would be carbon dioxide's partial pressure? Right? What would be carbon dioxide's partial contribution to the total air pressure of 760? If it makes up 13.5% of the air, then it would contribute 13.5% to the total pressure. So carbon dioxide's partial pressure would be 100 millimeters of mercury. All right, and now we put it into this cylinder, and there's fluid inside of the cylinder. And to start off with, within that fluid, there is no carbon dioxide at all. So the partial pressure of CO2 within the fluid is 0. So to start off with, the partial pressure of carbon dioxide within the air is 100. The partial pressure of carbon dioxide within the fluid or the water is 0. So there's clearly a partial pressure gradient here. Carbon dioxide wants to move from the air in the cylinder, where the partial pressure of carbon dioxide is 100, into the fluid or the water in the cylinder, where the partial pressure of carbon dioxide is nothing. Okay, so carbon dioxide wants to move from the air into the water. And that's exactly what it does. Okay, but what you'll see, yet again, is as carbon dioxide moves from the air into the water, the partial pressure of carbon dioxide within the air doesn't fall, while the partial pressure of carbon dioxide within the water rises, right? And they're actually at equilibrium when both of them, the partial pressure of carbon dioxide within the air and the partial pressure of carbon dioxide within the water, they're both at 100. And perhaps you have the same question, which is, how can you end up in a situation where the partial pressure of carbon dioxide within the air is 100 and the partial pressure of carbon dioxide within the fluid is 100? Meaning, how can you end up in a situation where carbon dioxide moved from the air into the fluid for logical reasons, right? It went down its partial pressure gradient. Oxygen moved from the air where the partial pressure of carbon dioxide was 100 into the fluid where the partial pressure of carbon dioxide was nothing. Okay. But then, how did carbon dioxide move from the air into the fluid, drive the partial pressure of carbon dioxide within the fluid up, but then the partial pressure of carbon dioxide within the air didn't fall at all, right? The partial pressure of carbon dioxide within the air stayed at 100 millimeters of mercury, and the partial pressure of carbon dioxide within the fluid went up to 100 millimeters of mercury. Why didn't the partial pressure of carbon dioxide within the air fall at all? And the answer, just like with oxygen, is that carbon dioxide is non-polar and water is polar, right? So yes, carbon dioxide is going to move from the air into the fluid. It's going to move down its partial pressure gradient, but you don't actually need many carbon dioxide molecules to move from the air into the fluid to drive the partial pressure of carbon dioxide within the fluid up to 100. Carbon dioxide and water do not exist together very well. Okay, carbon dioxide is very nonpolar, water is very polar. So any carbon dioxide molecule that comes into the water, it bounces around, shoots around like crazy, bounces all over the place because the carbon dioxide is nonpolar and the water is polar. So you don't actually need very many carbon dioxide molecules to move from the air into the fluid to very quickly drive the partial pressure of carbon dioxide within the fluid up to 100. Because those CO2 molecules will bounce all around, all over the place, the few of them that go in there, and very easily a couple of them will drive the partial pressure of carbon dioxide within the fluid up to 100. And thus, so few carbon dioxide molecules actually left the air that the partial pressure of carbon dioxide within the air doesn't change at all. You end up with a situation where the partial pressure of carbon dioxide within the air is 100 and the partial pressure of carbon dioxide within the fluid is 100. Right? That's what you end up with. And also, very importantly, the concentrations are vastly different, right? when their partial pressures are at equilibrium, meaning the partial pressure of carbon dioxide within the air is 100 and the partial pressure of carbon dioxide within the fluid are 100, the concentrations are vastly different. The amount of carbon dioxide within the air is infinitely higher than the amount of carbon dioxide within the fluid, even though their partial pressures are at equilibrium. Yet again, this is Henry's law. It tells us that a gas within the air and a gas within the fluid, or a fluid, right, can have the same partial pressures. The partial pressure of carbon dioxide within the air can be 100, and then the partial pressure of carbon dioxide within the fluid will be 100. In fact, this will happen because of this partial pressure gradient that exists. Carbon dioxide will move from the air into the fluid, and they'll both end up with partial pressures that are exactly the same. But yet their concentrations will be vastly different. There will be much more carbon dioxide within the air than there will be within the fluid. And yet again, that's because so few carbon dioxide molecules actually needed to go into the fluid to drive the partial pressure of carbon dioxide of the fluid up to the same as the partial pressure of carbon dioxide within the air. So these are the two examples that you looked at. You looked at two different cylinders. You filled up both of the cylinders with air. Okay, the total air pressure in both cylinders, let's say that's cylinder number 1, here's cylinder number 2, right? The total air pressure in both of them was 760, okay? The difference was the amount of, the difference between the two cylinders was the gas concentrations. So in cylinder number 1, 13.5% of the air was made up of oxygen, so the partial pressure of oxygen within the air, O2, was 100. And in cylinder number 2, 13.5% of the air was made up of carbon dioxide. So, by consequence, the partial pressure of carbon dioxide within cylinder number 2 was 100. Right? So again, you basically have two identical cylinders. Cylinder number 1, the partial pressure of oxygen within the air is 100. Cylinder number 2, the partial pressure of carbon dioxide within the air is 100. And in both cylinders, there's water. So in both cylinders, you create a partial pressure gradient because initially in cylinder number 1, there's no oxygen within the water. So the partial pressure of oxygen within the water is nothing. And in cylinder number 2, there's no carbon dioxide within the water to start off with, so the partial pressure of carbon dioxide within the water is nothing, right? So there's a partial pressure gradient in both cylinders, and what happens in the first cylinder, oxygen moves from the air into the fluid. In the second cylinder, carbon dioxide moves from the air into the fluid, right? Until they both reach equilibrium. When is that going to happen? Well, that's going to happen when the partial pressure of oxygen within the air is 100, and the partial pressure of oxygen within the fluid is 100, right? That's going to be cylinder number 1. We can get rid of this. Okay? And in cylinder number 2, what happens is we're going to end up with the same thing. The partial pressure of carbon dioxide within the fluid will end up being 100, and the partial pressure of carbon dioxide within the air will end up being 100. Okay? That's cylinder number 2. Now they're both at equilibrium. And in both cases, it kind of looks like the exact same thing happened. In both cases, you have oxygen, which is nonpolar, and you have carbon dioxide, which is nonpolar. And then in both cases, you have water, which is polar. So in both of these cases, the gas, be it oxygen or carbon dioxide, doesn't exist with the water very well because the gases are nonpolar and the water is polar. So in both cases, you don't actually need very many gas molecules, be it oxygen or carbon dioxide, to go into the fluid to drive the partial pressure of the fluid up to 100. Right? Because both oxygen and carbon dioxide will bounce around like crazy in the fluid and very easily drive the partial pressure of the fluid, be it the partial pressure of oxygen within the fluid or be it the partial pressure of carbon dioxide within the fluid, up to 100 very, very quickly. So in both cases, you're at equilibrium when the partial pressure of oxygen and the partial pressure of oxygen within the air and the partial pressure of oxygen within the fluid are at 100, and when the partial pressure of carbon dioxide within the air and the partial pressure of carbon dioxide within the fluid are at 100. In neither case does the partial pressure of the gas in the air drop at all, because so few of the gas molecules, be it of oxygen or CO2, actually went into the water to drive the partial pressure of either oxygen or carbon dioxide within the water up to 100. And yet again, in both instances, there's going to be much more gas in the air than there is in the fluid. There's going to be much more oxygen within the air in terms of a concentration, in terms of a number, than there is in the fluid. There's going to be much more carbon dioxide within the air than there is carbon dioxide within the fluid. Yet their partial pressures will be at equilibrium. So is there any difference? Like, what was the point of comparing oxygen and carbon dioxide? And the answer is yes, there's a difference. Okay. Oxygen and CO2 are both nonpolar, but CO2 is more polar than oxygen is. Okay. What I mean by that is oxygen and carbon dioxide are both very nonpolar gases, but CO2 has more polarity than oxygen does. All gases, no matter how nonpolar they are, have some degree of polarity. We consider oxygen and CO2 both to be very nonpolar gases, but what I'm saying is CO2 has more polarity to it than oxygen does. So that's where the difference comes into play here. Okay? Because on the surface, it looks like everything is exactly the same. Right? The partial pressure of oxygen within the air is 100. The partial pressure of oxygen within the fluid is 100. The partial pressure of carbon dioxide within the air is 100. The partial pressure of carbon dioxide within the fluid is 100. So where is there any difference whatsoever? And the difference is the amount of the gases that actually exist within the fluid to drive the partial pressure up to 100. For carbon dioxide to drive the partial pressure of the fluid up to 100, meaning to drive the partial pressure of carbon dioxide within the fluid up to 100, you actually need more CO2 molecules to go into that fluid compared to oxygen. For oxygen to drive the partial pressure of oxygen within the fluid up to 100, you need less molecules of oxygen to actually go into that fluid to accomplish this compared to CO2. That's actually what this is trying to show you, right? Everything's the same, it looks like, right? The partial pressure of oxygen within the air is 100. The partial pressure of oxygen within the fluid is 100. The partial pressure of carbon dioxide within the air is 100. The partial pressure of carbon dioxide within the fluid is 100. So everything looks identical, but look at the number of oxygen molecules within the fluid compared to the number of carbon dioxide molecules within the fluid. There's less molecules of oxygen within the fluid compared to the number of molecules of carbon dioxide within the fluid. Yet, both fluids have a partial pressure of 100. This one has a partial pressure of oxygen of 100. This one, cylinder 2, has a partial pressure of carbon dioxide of 100. To accomplish that, though, comparing the two gases, you need less molecules of oxygen to go into a fluid to drive the partial pressure up to 100 compared to carbon dioxide, where you need more molecules of carbon dioxide to go into the same size, the same amount of fluid to drive the partial pressure of carbon dioxide within that fluid up to 100. And you think, well, why is that? And the answer is it's quite simple. Oxygen is more nonpolar. The carbon dioxide is a little bit more polar than oxygen, which is more nonpolar. They're both nonpolar, but carbon dioxide is a little bit more polar than oxygen is. So, since oxygen is more nonpolar, oxygen bounces around in fluid more than carbon dioxide does. Carbon dioxide bounces around a lot in fluid, but it doesn't bounce around as much in fluid as oxygen does. And that's because carbon dioxide has more polarity than oxygen does. Okay? So because oxygen is more nonpolar than carbon dioxide is, carbon dioxide is more polar, that means that oxygen exists in water less than carbon dioxide can exist in water. Oxygen will bounce around in fluid more than carbon dioxide will. So you need less molecules of oxygen to go into the fluid to bounce around enough to drive the partial pressure of oxygen within the fluid up to 100, compared to carbon dioxide, where carbon dioxide just exists in the water a little bit better. It doesn't exist good in the water, but it exists better in the water compared to oxygen. So you need more molecules of carbon dioxide to go into the water to bounce around enough to drive the partial pressure of carbon dioxide within the water up to 100. That's the difference between these two gases. The point of comparing them at all was to show you this, because it's going to become relevant in future discussions. Within these two cylinders, cylinder number 1 has a partial pressure of oxygen within the fluid of 100. Within cylinder number 2, there's a partial pressure of carbon dioxide within the fluid of 100, which seems that would be, almost identical, but it's not, right? Actually, in cylinder number 1, there's less oxygen molecules that had to go into that fluid to drive the partial pressure of oxygen within the fluid up to 100, compared to cylinder number 2, where there was more molecules of carbon dioxide that needed to go into the fluid to drive the partial pressure of carbon dioxide within the fluid up to 100. Now, please don't get it twisted. In either case, did many gas molecules need to go into the fluid to drive the partial pressure up to 100? Neither case required many gas molecules to actually go into the fluid, but less molecules of oxygen need to go into a fluid, in this example, to drive the partial pressure of oxygen within that fluid up to 100, compared to carbon dioxide, where you do, even if it's not that many more, you still need more carbon dioxide molecules to go into the same volume, the same size fluid to drive the partial pressure of that fluid up to 100. And after all that craziness, we're finally back to gas exchange at the level of the alveoli and the pulmonary capillaries. Okay? So what do you have? You have air that exists in the alveoli. The partial pressure of oxygen within the air in the alveoli is 100. And now the blood is traveling past the alveoli, right, as it's traveling through the pulmonary capillaries. Okay, what's going on with the blood? Inside of the blood plasma has a partial pressure of oxygen of 40 millimeters of mercury. There's enough oxygen within the blood plasma to drive the partial pressure of oxygen within the blood plasma up to 40 millimeters of mercury. Okay, so there's a partial pressure gradient, right? The partial pressure of oxygen within the air in the alveoli is 100, and the partial pressure of oxygen within the blood plasma in the pulmonary capillaries is 40. So what happens? Oxygen wants to move down its partial pressure gradient. Oxygen wants to move from the air in the alveoli into the blood plasma within the blood in the pulmonary capillaries. And that's exactly what it does. And what ends up happening here is both of them end up reaching 100. And that's why I needed to go on that incredibly long divergent kind of tangent there. Because I needed to explain to you why the partial pressure of oxygen within the air in the alveoli and the partial pressure of oxygen within the blood plasma both reach 100 without the partial pressure of oxygen within the air in the alveoli dropping at all. And it's all because of Henry's law. What is the blood plasma made up of? The blood plasma is made up of water. What is water? H2O. What is H2O? It's very polar. Okay. What is oxygen? Oxygen that's in the air in the alveoli is very nonpolar. So what's happening here is oxygen is moving from the air in the alveoli, where the partial pressure of oxygen within the air is 100. And where's it moving to? It's moving into the blood plasma, which is water, right? Where the partial pressure of oxygen within the blood plasma, which is water, is 40. Right? So oxygen moves from the air into the blood plasma, moves down its partial pressure gradient. And very quickly, you only need a very small number of oxygen molecules to move from the air in the alveoli into the blood plasma to drive the partial pressure of oxygen within the blood plasma up to 100. And this is all because of Henry's law, right? Oxygen is incredibly nonpolar. The blood plasma is made up of water, which is incredibly polar. They don't exist with each other very well. So very few molecules of oxygen actually need to move from the air in the alveoli into the blood plasma within the pulmonary capillaries in order to drive the partial pressure of oxygen within the blood plasma of the pulmonary capillaries up to 100. Because that oxygen that moves from the air in the alveoli into the blood plasma within the pulmonary capillaries, it'll bounce around like crazy, and it very quickly drives the partial pressure of oxygen within the blood plasma up to 100. And then they're at equilibrium. And you say, well, why didn't the partial pressure of oxygen within the air in the alveoli drop at all? And the answer is, well, because like no oxygen actually has really left the air in the alveoli to go into the blood plasma yet. You don't need very many oxygen molecules to actually move from the air in the alveoli into the blood plasma to drive the partial pressure of oxygen within the blood plasma, which is actually water, up to 100 millimeters of mercury. So what you end up here with is exactly what we went through. Except now you're actually applying this to real life. You end up with the partial pressure of oxygen within the air in the alveoli being 100, and the partial pressure of oxygen within the blood plasma that exists in the pulmonary capillaries being 100 as well. And so far, very few oxygen molecules have actually moved from the air in the alveoli into the blood plasma, because not very many needed to in order to drive the partial pressure of oxygen within the blood plasma up to 100. So that brings us to the point of, what's the point of driving the partial pressure of oxygen within the blood plasma up to 100 at all? Because so few molecules of oxygen have actually moved from the air in the alveoli into the blood plasma to accomplish this. That can't possibly be all that happens when we reoxygenate blood. There's got to be another reason that we do this, and there is, and it's incredibly important. And we're going to get into it into the next and we're going to get into it in the next lecture. You want to drive the partial pressure of oxygen within the blood plasma up to 100 to influence the other thing that makes up the blood, which is, or are, the red blood cells, the erythrocytes. Changing the partial pressure of oxygen within the blood plasma is going to have an enormous influence over the behavior of certain proteins that exist within our red blood cells. And that is what we will talk about in the next lecture.